Okay, we are back. There was an innocent-looking homework assignment that you were supposed to do over the weekend, and the assignment was first to watch this video that was about 20 minutes long of me solving a so-called hard induction problem. So this is, I think, significantly more difficult than the induction problems that we did together in class last week. It was an inequality, and when proving inequalities, it's not always so obvious what to do because it's not just a simple matter of, adding on the extra term or something like that. So this really exhibits the power of induction to prove things that I'm not sure how you would do otherwise. So here we go. I have this problem. Then you have to do for homework 3 problems, all of which were hard. This one maybe was okay, but it's very, very not obvious what to do. Okay, we begin. I have this fact that I need to prove, that 4/3 to the n is bigger than n for n greater than or equal to 7. Alright, I think maybe like the hardest part of this, or not the hardest part, but one annoying thing is that it's just not obvious at all that this is true for n greater than or equal to 7, except for just doing it. So, okay, I mean I can just compute for various values of n and 4/3 to the n. See if I can kind of squeeze this in here. Well, when n is 1, I do have that 4/3 is bigger than 1, so that's good. But then, when I get to 2, now this is 16/9, which is now less than 2. So my number becomes now, the left side becomes, not bigger than the right side again. And now I think when I continue multiplying by, this is like 64 over 27. That's less than 3. And multiplying by 4 again, 126, that's 256 over 81. So I know my powers of 2 well enough, so I can't really tell whether that's going to be less than 4 because it's 320-ish. Alright, so 5, 6, 7. What's this? It's going to be 5 to 1,024 over 243. That seems like about 4-ish, so I think that's also less than 5. And then this number just keeps getting bigger and bigger, right? See, am I doing this right? 4 to the 5th, yeah, is 1,024, so 2048, so this is 4,096. Is this true? Man, this number is gigantic. Sorry, just sort of thinking about what I'm doing here. Yeah, I guess so. Over, I don't even know, that's 729. That's about the end of my knowledge of powers of 3. And now I guess this needs to be multiplied by 4 like even one more time. So that's 8192 and then like 16384. I believe that is right. I don't recall these numbers being so big, but I guess I haven't done this problem in a while. Is it just true that 4 to the 7th is 2 to the 14th, and 2 to the 14th will be 2 to the 10th times 2 to the 4th. So yeah, this is just really true, and this is probably even the right answer because 96 times 4 is 384. And so everything's good. And then 729 times 3 is a big number. Man, I don't even know. Let's see, it will be 2187. I am reasonably confident about that. And here I honestly can't tell whether this is true or not. So here this is true, but then it becomes false. And just by eyeballing it, it still appears to be false. Yeah, and this will be roughly 43 something, so it's false, but then, let me just make sure I've done 3 to the 7th right. 21 and 3 times 29 is 87, yeah. So then I guess this is true. I need to sort of confirm that or something. That's just not obviously true at all. Oh, this is supposed to be bigger. Yeah, so here just by kind of eyeballing it, right, 7 times 21 is going to be sort of something on the order of 14,000, and that is going to be less. So I claim that this is true. Okay, if you really want to do it out, I guess we might as well. if you take 2187 and you multiply it by 7, what do you get? 9. Carry the 4. 8 times 7 is 56. So that's 60. So I got a 6 up there. 7 and 6 is 13. Carry the 1. So it is in fact 15309. Therefore, I'm now going to say that 16384 over 2187 is in fact bigger than 7. That's just confirmed because 16,384 is bigger than 15,309. Okay, not surprising that this is growing linearly and this is growing exponentially, so we feel that an exponential function is going to grow very, very fast and eventually will overtake any linear function. In fact, it will overtake any polynomial eventually. So it will certainly overtake this linear function. And so we did a problem almost exactly, the problem that I had you watch on the video was kind of a very similar setup. It was a exponential function sort of overtaking a quadratic eventually. And okay, just brute force calculations have shown, even if they hadn't given me this upper bound of 7, I could have just experimented and sort of kept going until I get to the point where it becomes true. Now I feel that because of this exponential growth, I feel that it's going to now stay true. So that is exactly what we need to prove. Okay, let's go. How are we going to do this? Well, the base case is what we just did already. The base case is to confirm that this is true for some small number, in this case 7. So, okay, so I guess I'm just going to call this done, right? We already just computed that 4/3 to the 7 is greater than 7. So base case confirmed. So the base case is the case n equals 7. Okay, and now we are going to make our inductive hypothesis. Very concerned about my whiteboard staying perfect. I see like a scratch, which is, alright, well, whatever. Okay, I will now make my inductive hypothesis. And my inductive hypothesis is that this is true for some k. So assume temporarily that 4/3 to the k is greater than or equal to k for some k greater than or equal to 7. Okay, and well, now what I need to show is that 4/3 to the k plus 1 is greater than or equal to k plus 1. Alright, and well, here we go. This is the whole logical structure. Hopefully this part you understand. If whenever this is true, it's true for the next number, and it's true for 7, then I will be able to show that it's true for every number from 7 and up. Okay, so it's just a matter of now how am I going to do this? All right, and there are lots of ways to do this. This one is easy enough that you might just come up with the answer kind of immediately, and usually textbooks and teachers just kind of do something and then you're just expected to do a similar thing. But I think I want to teach this with a kind of systematic approach in mind. So my systematic approach is to manipulate the thing that you are trying to prove, to make it look as much as possible like the thing that we know. And so here, 4/3 to the k plus 1, well, that's just 4/3 times 4/3 to the k is greater than k plus 1. And because I am kind of doing some combination of guesswork, looking ahead, looking back, manipulating the thing I am trying to prove, I think it is important to keep it all straight by continuing to write the word show next to your algebra to remind yourself that you haven't proven this is true, you're just restating something that you need to show. Okay, and now, let's see, are we ready yet? I think we are, no, I think now, okay, there's a bunch of different ways to do this, but the piece that I want to kind of get rid of is this 4/3 to the k. I don't like 4/3 to the k. That sounds hard, because that's kind of like an exponential function. So now, maybe some kind of experimentation is required here, although this is not the only way to do this. But if you now multiply both sides of this by 3/4, again, I won't just write that on the paper by itself, but I will write the word show next to it to remind myself that this is something that I am trying to prove. Okay, well now I have an idea. And this is my sort of thing that I came up with for teaching this. This is the kind of no need, wish sort of model of thinking about these proofs by induction. So I'm going to put a red box around this. This is something that I know to be true because I have assumed it. It's my inductive hypothesis. This is the thing that I need or want. I think some years I call it want. But I need to show this. In order to complete the proof, I need to show this thing in the blue box. Okay, and now what we're going to do is we're going to create a bridging inequality. We're going to create an inequality which, if it were true, would enable me to get from the thing that I know to the thing that I need. And here, I think I see it. If k were greater than or equal to 3/4 k plus 1, I wish this were true. Why do I wish this were true? I wish this were true because if I knew this somehow, then I could say that 4/3 to the k is greater than k, which is greater than 3/4 times k plus 1. And that would give me then the thing in the blue box. Alright, so this takes some kind of practice and discipline, but alright, there it is. I will put a purple box around this, and I will call it my wish. And alright, now I have reduced this entire problem to the seemingly simpler problem of just proving this wish. Okay, so let's just prove the wish. Well, I'm going to prove the wish by working backwards. So I multiply both sides by 4, and that says that 4k is greater than or equal to 3k plus 1. So 4k is greater than or equal to 3k plus 3. And this says, therefore, by subtracting 3k from both sides, that k is greater than or equal to 3. And I just know that k is greater than or equal to 3. So I've kind of reduced the thing I'm trying to prove down to some sort of very, very obvious low-level fact. And now I'm kind of done. Well, I'm not done. I'm done with my scratch work. Now comes the actual proof. And when we're going to do the actual proof, we are going to now prove the wish. So, okay, how can I prove the wish? Well, I should start with the one thing that I know about k. I know that k is greater than or equal to 7. That is just a fact about k, because it's my inductive hypothesis holds, for some k greater than or equal to 7. Alright, well if k is greater than or equal to 7, then of course it follows that k is greater than or equal to 3. This is a sort of a strange thing, I think, for students to write on the paper, because we're not just kind of manipulating mindlessly some sort of statement. Instead, we're doing a kind of thoughtful inference. We're making an inference, but of course this inference is valid. It just is true that if something is greater than or equal to 7, it's greater than or equal to 3. That's just a fact. Why would I go from this step to this step? Sure, it's true, but that's a strange thing to do. Well, I do that because I've done this backward scratch work and I know that that's the particular algebraic form I want my statement to be in. Okay, so continuing now, what am I going to do? I'm going to add 3k to both sides. So that's not something I would have necessarily thought of, but there it is. I add 3k to both sides. Why would I do something like that? Well, because I can factor 3 out of the right side, and then I can divide by 4. So k is greater than or equal to 4/3 k plus 1. Okay, so in that case, it was pretty easy for me to do what I needed to do. What did I do? I just proved the wish. So I wished that something were true, I worked backwards to see why it is true, and now I've proved that the wish is true from only the fact that k is greater than or equal to 7. Okay, and great. Now, I also have, so I'll just write something like, also, by inductive hypothesis, what do I know? I know that 4/3 to the k is greater than or equal to k. It's not really an also, because this is really sort of like one big statement. It's that 4/3 to the k is greater than or equal to k, and that k is greater than or equal to 7. Sort of both, that's my inductive hypothesis, both of those kind of together. So anyway, so maybe I'll put like a green box around this or something, because both of these together are the very thing that I assume in my inductive hypothesis. And so I'm sort of using both of those facts. Okay, well, yeah. Now I just combine these two facts together. And I think I wrote it in the opposite order, but it doesn't really matter. What do I know? I know by my inductive hypothesis that 4/3 to the k is greater than or equal to k, but I know by the wish that k is greater than or equal to 3/4 k plus 1. So, by the transitivity of greater than, I know that 4/3 to the k is greater than or equal to 3/4 k plus 1. So, multiplying both sides by 4/3 gives me 4/3 times 4/3 to the k is greater than k plus 1, and therefore 4/3 to the k plus 1 is greater than or equal to k plus 1, and that is exactly what I needed to show right here. Okay, great. Great. And then, what was I going to say next? Oh yeah, so now final concluding remarks. My concluding remarks are just summarizing the entire process. I know that 4/3 to the 7th is greater than 7. And what else do I know? I know that for all k greater than or equal to 7, the following holds. If 4/3 to the k is greater than or equal to k, that was my inductive hypothesis, then 4/3 to the k plus 1 is greater than or equal to k plus 1. So, by the principle of mathematical induction, if this is true for 7, and whenever it's true for k, it's true for k plus 1, for k greater than or equal to 7, then by mathematical induction, 4/3 to the n is greater than or equal to n plus 1 for all n greater than or equal to 7. Okay, I think that is quite hard. Coming back to do the next one in a second. Okay, we are back for number 36. Number 36 says, prove that 1 over root 1 plus 1 over root 2 plus 1 over root 3 all the way up to 1 over root n is greater than or equal to root n for n greater than or equal to 2. This problem is very hard. I mean, maybe you didn't even think that were problems so hard, in this entire Precalc textbook. Whew, what are we going to do? How are we going to do this? Well, we're going to do it by induction. And, okay, the sort of first step, I think, might be, just so we don't go crazy, is to nickname the whole left-hand side of this equation. Let's just call this a sub n, so I can refer to that in the future. And okay, let's just jump right into the base case, and let's just, or the base step. People do say base case though, and let's confirm that this is even true for n equals 2, which is just not obvious. What is it? What is this inequality saying for n equals 2? Well, it's saying that 1 over root 1 plus 1 over root 2 is greater than or equal to root 2. And I don't find that to be immediately obvious, at all. So let's see if this is true. Is this true? Well, this is really just saying 1 plus 1 over root 2 is greater than or equal to root 2. In other words, I'm manipulating both sides of the inequality in a well, so far I haven't really done anything. I just rewrote the 1. Now, is this becoming more clear? Not really. This looks plausible, but I'm not really sure about this at all. Okay, one thing that we might do is multiply both sides by root 2. And the thing about multiplying both sides by root 2 is that it preserves the inequality, and it preserves the inequality kind of bidirectionally. Which is to say, what I'm going to do now is multiply both sides by root 2, which gives me root 2 plus 1 is greater than or equal to 2. And okay, that's certainly a simpler statement, so I am sort of making some progress. But crucially, the idea is that, yes, if this is true, then multiplying both sides by root 2 makes it, still true. But also, if this statement were true, and I divided by root 2, then the inequality also holds. In other words, multiplying both sides of an inequality by root 2 doesn't change the truth of it, and dividing both sides of an inequality by root 2 doesn't change the truth of it either. Therefore, I'm going to draw this kind of double arrow, which is the smooth way of saying, this statement is true if and only if this statement is true. And if you throw in, sort of double arrows kind of as you go, then what we're really doing is we're sort of reducing this inequality to something kind of more obvious. All right, what am I going to do now? I'm going to subtract 1 from both sides. So that is root 2 is greater than or equal to 1. And once again, subtracting a number from both sides preserves the inequality, but adding a number to both sides also preserves the inequality. So if this is true, then this is true, then this is true. And okay, here, this is pretty obviously true, but if you want to do sort of one more thing, which is to square both sides, well, then we get that 2 is greater than or equal to 1, which is just true. And therefore, by sort of pursuing only equivalence, inequality preserving operations, I should say, then I don't need to kind of rewrite this, because since 2 is greater than or equal to 1, then take the square root of both sides, which is completely legitimate if everything is positive, then add 1 to both sides, then divide by root 2, and that shows that this is true. Okay, so this is just kind of a general math strategy for proving inequalities. It's often the way to do it, simple numeric inequalities, is to kind of start with the thing you're trying to prove and then just sort of manipulate it down to something which is true. And as long as every step is reversible, which it is in this case, then you're actually just done and you don't need to rewrite it. Okay, this is probably more work than you showed, but this actually is giving me some kind of experience now that I'm hopefully going to use here in the inductive step. Okay, time for the inductive step. Well, let's go. In the inductive step, I'm going to have to write small, even though I have this beautiful giant board, which I've already slightly ruined with a scratch. Very sad about that. Alright, in my inductive step, I'm going to assume that this is true for some k greater than or equal to 2. So let's just assume, and here I'll use my shorthand, that a sub k is greater than or equal to root k for some k greater than or equal to 2. Okay, and then what I need to do is to show that it's true for the next number. So what I need to do is I need to show that a sub k plus 1 is greater than or equal to root k plus 1. Okay, how am I going to do this? Well, alright, what is it that I really need to show? What is a sub k plus 1? Well, a sub k plus 1 is just, and now I write sort of very small, 1 over root 1 plus 1 over root 2 plus all the way out to 1 over root k plus 1 over root k plus 1. In other words, and this is why I use a different variable, k, in other words, a sub k plus 1 is just what you get when you plug k plus 1 in for n in the big expression on the left. Okay, and so yeah, we just keep going all the way up to, I don't stop at k, I stop at k plus 1. Okay, and maybe you don't even need to write this step, because once you've done a couple of these, you sort of see what's going on, which is that all of this is actually just a sub k. In other words, with each increasing, as n gets bigger and bigger, each time I add sort of one more term to this sum, and so the k plus first, the sort of, okay, yeah, a sub k plus 1 is just going to be a sub k plus the one extra term that you added on to the end. Okay, therefore, making use of my shorthand notation, a sub k plus 1 is really just a sub k plus that extra little thing that we added on to the end. Okay, and here, and maybe you could have gone, straight to this if you just saw that that was a sub k plus 1. But if you didn't see it, now you do. Okay, well now we are again going to pursue this kind of no need, want strategy. I can't remember what my color coding was, but I'm going to put a box around this and call this the no. So I know that a sub k is greater than or equal to root k because I've assumed that. That's part of the inductive hypothesis. And then what I need to do is prove this thing here. How am I going to prove this thing here? Well, to me, the thing to do seems to be to make it look as much like the thing that I know as possible. And here, the kind of expression that's really annoying is this sum of, reciprocals of square roots. And so what I'm going to do is I'm going to isolate that on one side. And so what I really need to show is that a sub k is greater than or equal to root k plus 1 minus 1 over root k plus 1. Okay, if I can show that, then I'm just done. Okay, so this is the thing that I need. And I will put a big box around this, and I will write, need. I need this to be true. And, okay, this is the moment that is so difficult, because you need to now decide how can I get from this thing that I know to this thing that I need. Somehow I have to get from the thing in the red box to the thing in the blue box. How are we going to do it? Well, is there some sort of bridging inequality which, if it were true, would help me? And I think the answer is yes. If it were true that, hopefully I do this right, is it really okay? Yeah. If it were true that root k were greater than or equal to root k plus 1 minus 1 over root k plus 1, then that would be amazing. Why? Because if I somehow knew this, so I wish that this were true, because if this were true, then I would combine it with my inductive hypothesis, and I would be able to say that a sub k is greater than or equal to root k, which is greater than or equal to root k plus 1 minus 1 over root k plus 1. And that would give me the thing in the blue box that I need. Okay, so I put a purple box around this, and now my entire world becomes just this. Prove this wish. If I can prove this wish, then I will be basically done. And proving this wish doesn't seem too impossible because this wish is just sort of like algebra, so to speak. Okay, so how can we prove this wish? Well, the first thing I'm going to do is, I'm going to manipulate this inequality, sort of inspired by what happened over here. Now it seems like the good step to do would be to, once again, get rid of fractions. So let me just multiply through by root k plus 1. So if I do that, then I get root k plus 1 is greater than or equal to, well, when I multiply root k plus 1 by root k plus 1, I just get k plus 1. And now this becomes 1. Okay, in other words, multiply through by that denominator to get rid of all the denominators. Well, this looks kind of nice. This now means all I need to do is prove that root k times k plus 1 is greater than or equal to k. And once again, what did I do? I'm not going to, I'll just keep going. Why is this true? That's not obviously true, but it's starting to look kind of plausible. Well, if I square both sides, then I get k plus 1 is greater than or equal to k squared. And squaring both sides is a reversible step as long as everything is positive, which it is in this case. Okay, well, this is k squared plus k is greater than or equal to k squared. And that's true as long as k is greater than or equal to 0. And so, in fact, this wish is just true, as I have indicated with this kind of backwards logic. Okay, because everything that's going on here is so sort of clear and chaotic and backwards and everything, I do think it's important to do the actual proof. So what does the actual proof look like? All right, we begin with the, this time I'm going to write it in the correct way. So by my inductive hypothesis, what do I know? I know that a sub k is greater than or equal to root k for k greater than or equal to 2. Okay, well, since k is greater than or equal to 2, then that means that k is greater than or equal to 0. Okay, I won't repeat my whole speech because I think you get it now, right? It's a strange thing to do, but it is true that if k is greater than or equal to 2, then it's greater than or equal to 0, but greater than or equal to 0 is what I want. And now I just reverse all the steps, right? Add k squared to both sides. That gives me k squared plus k is greater than or equal to k squared. Hopefully I'm not in the way here. You can rewrite this slightly as k plus 1 is greater than or equal to k squared. Take the square root of both sides, which is legitimate as long as everything is positive, which it is. Well, it is this left side, both sides here just, well, okay, everything is positive, everything is greater than or equal to 0, I guess. So that's legit. So taking the square root of both sides, I get root k plus 1 is greater than or equal to k. Now I rewrite this square root as like root k plus 1. And now I have to do something that I never would have thought of had I not already done this problem, which is to just throw in a little plus 1 minus 1 there on the right hand side. Then I am going to divide both sides of this inequality by root k plus 1. I might even just throw in a little, like, algebra 1 style in blue. That's what I'm doing. I'm dividing through by root k plus 1. Well, root k plus 1 over root k plus 1 is just root k. And over here, what happens when I divide k plus 1 over root k plus 1? Well, that just becomes root k plus 1 minus 1 over root k plus 1. Okay, because this is just like, right, like n, well, I think you guys are all good on this, right? Yeah, k plus 1 divided by root k plus 1 is just root k plus 1. Okay, and is that the wish? It is the wish. So I am now just super happy because I proved my wish. And now I combine these two statements together, my inductive hypothesis and my, which is right here, and my wish, which I just proved. And together they tell me that a sub k is greater than or equal to root k, which is in turn greater than or equal to root k plus 1 minus 1 over root k plus 1. And, okay, by transitivity then, I have that a sub k is greater than or equal to root k plus 1 minus 1 over root k plus 1. And, okay, why is that good? Because if I add that to both sides, I get that a sub k plus 1 over root k plus 1 is greater than or equal to root k plus 1. And this just is a sub k plus 1. And therefore, now I am really just done. So, there it is. Okay, here I'm getting lazy and I don't feel like writing the concluding statement, and I also ran out of room, so there it is. But we did everything, right? We started with our inductive hypothesis, and we proved that if it's true for k, it's true for k plus 1. Okay, so I think this is quite hard. Be right back for the third problem. Okay, we are back for the third problem, the third one of these so-called difficult induction problems. And I think this is also quite difficult. This is now not a statement that two expressions are equal, nor is it a statement that two of an inequality between two algebraic expressions, but is instead some kind of number fact. Here is this number fact. The number fact is that for, here it's understood that n is a positive integer, that if you raise n, if you raise 2 rather, to some sort of particular odd power, and you raise 3 to that same odd power, that together, that is a multiple of 5. Okay. This is not obvious at all. And I think requires some preliminary exploration. Okay, let's kind of explore. Well, okay, maybe before we do anything else, maybe we should just sort of nickname this entire expression, a sub n. So let a sub n refer to, this expression over here. And then also I'll introduce a little bit of notation. I used this notation much earlier in the semester on the proof of the rational root theorem on that day, but I think I said that this video is optional, so maybe you've never seen this symbol before. It's the divides symbol. So what is it that we really need to prove? We really need to prove that a sub n is a multiple of 5. So what we need to do is we need to prove that 5 divides a sub n. For I guess here the understood case is that n is greater than or equal to 1. Okay, right. Let's check to see if it is true. What is, so let's now just check it for n equals 1. Well, what is a sub 1? A sub 1 just says, stick 1 in for n. So that's 2 to the 1 plus 3 to the 1. Okay, well, that's just 5. And so indeed, 5 does divide a 1. 5 goes into, think of that as just goes into evenly. Okay, let's check it again. Let's check it for n equals 2. Because that one was kind of unsatisfying or something. Okay, well, if n is 2, now what is a2? A2 is going to be, well, now I stick a 2 in for n, so that gives me 3. So it's just sort of like the next odd number. Every odd number can be expressed in the form 2n minus 1, as long as you start counting at n equals 1. Every positive odd number. So think of this as just skipping by 2 every time. So these are just always odd. These are always odd up here. So anyway, this is now 2 cubed plus 3 cubed. And just from looking at it, it's not obvious to me that 2 cubed plus 3 cubed should be a multiple of 5. But in fact, well, what is 2 cubed plus 3 cubed? It's 8 plus 27, and that's 35. And, what do you know? That is a multiple of 5. So 5 also divides a sub 2. 5 goes into 35. Okay, so having done this kind of preliminary work, maybe now we will try to just prove it. Okay, so let's just assume that, so I'm making my inductive hypothesis now. Okay, I guess I can just write it right here, right? So my base step is that a1 is 5, and so 5 does divide a1. I just kind of did that. We sort of did the base step already while we were just kind of playing around, and now I'm going to make my inductive hypothesis. So inductive hypothesis is to assume that 5 divides a sub k. Okay. So what I know is, and maybe this shorthand is not so helpful in this case, what is it that I know? What I know is that 5 divides 2 to the 2k minus 1 plus 3 to the 2k minus 1. That's what I know. Alright, and if you don't like this divides notation, then you just have to use words like, this is a multiple of 5. Same thing. Okay, what do I need to show what is the thing that I need to prove to complete the proof by induction? Well, I need to show that 5 divides a sub k plus 1. After all, that's what we're going to do. We're going to assume that a sub k is a multiple of 5, and we're going to show that when that's true, the next number is also a multiple of 5. Okay, so what is it that I really need to show? I need to show that this a sub k plus 1 thing, which is, and maybe now here is a good time to write it. What is a sub k plus 1? You have to be a little bit careful with your algebra. Well, a sub k plus 1 is just what you get when you stick k plus 1 in for n in this expression. So this is going to be 2 to the, I'm writing kind of big, 2 to the 2 times k plus 1 minus 1 plus 3 to the 2 to the k plus 1 minus 1. Somehow I have to show that that is a multiple of 5. Okay. There are a lot of different ways to do this. I think the simplest way is to just start. So let's just take this expression 2 to the 2 k plus 1 minus 1 plus 3 to the 2 to the k plus 1 minus 1. And let's just somehow show that it is a multiple of 5. So we sort of begin right here with a sub k plus 1. Show that this is a multiple of 5. Okay, well, first of all, I can do some little arithmetic up here. What is this? This becomes 2k plus 2 minus 1. So actually, this is like 2 to the 2k plus 1 plus 3 to the 2k plus 1. So that is interesting. That is, I don't like how I spaced this out. Well, okay, we'll see if we have enough room. So this is similar to, but different from the thing that I know. I'm going to just put like a big red box around this thing that I know because it's somehow going to play a role, right? I know this. I know that 2 to the 2k minus 1 plus 3 to the 2k minus 1 is a multiple of 5. And that's going to play a crucial role in this proof somehow. Okay, but this is not that. This is something else. What is the relationship between 2 to the 2k plus 1 and 2 to the 2k minus 1? Okay, well, you just use some exponent rules, right? What is this? This is just a bunch of 2's. How many 2's? You know, a lot of them. 2k plus 1 of them. Well, 2k plus 1 is like 2 more than 2k minus 1. So this is really like 2 squared times 2 to the 2k minus 1 plus 3 squared times 3 to the 2k minus 1. Okay, so this is either maybe extremely obvious to you or not, right, this is just basic exponent rules, right? When you multiply 2 to the m times 2, 2 to the p times 2 to the q, then you just add. And so, okay, hopefully you all agree. And maybe even, okay, so that's just that. Why did I choose to do this? What I essentially did was I just like factored a 4 out of this. I factored a 4 out of this because I want to be dealing directly with 2 to the 2k minus 1 because that's the thing I know about. And similarly, I know something about 3 to the 2k minus 1, so I'm making my expression look as much like the thing that I know as I can. Okay, so finally, there's sort of one more thing I can do before I have to start thinking. This is 4 times 2 to the 2k minus 1 plus 9 times 3 to the 2k minus 1. Okay, and now I have to do some thinking. Here is the thinking. What do I have here? I have this really ugly expression. I need to show, right here is this sort of moment where we now pause to do some deep thinking. This purple arrow is pointing to an expression, and I need to show that this expression is a multiple of 5. How can I show that this expression is a multiple of 5? Well, somehow it's going to depend on this thing that I know over here in the red box. What I know is that 2 to the 2k minus 1 plus 3 to the 2k minus 1 is a multiple of 5. Okay, so if you give me one of these and one of these added up together, that is a multiple of 5. One of these plus one of these is a multiple of 5. But I don't have one of these and one of these. I have 4 of these and 9 of these. one of these plus one of these is a multiple of 5. But I have 4 of them and 9 of them. Oh, now I see. Having 9 of something is like having 4 of something and 5 of something. So I can rewrite this as 4 times 2 to the k minus 1, to the 2k minus 1, plus, I now choose to think of having 9 of these as like having 4 of them and having an extra 5 of them. And now, I'm done. Because every pair of these added up together is automatically a multiple of 5. And now I have 4 of these pairs and an extra something that is already automatically a multiple of 5. Okay, so now it's just a matter of just writing it out. What can I do? I can factor out a 4, and this is giving me 2 to the 2k minus 1 plus 3 to the 2k minus 1, and this is just 5. So, okay, running out of space, so that will influence how much I write now. But now I'm going to say, by my inductive hypothesis, I just know that this is a multiple of 5. This is a multiple of 5. Perhaps it's maybe nice to maybe write it out sort of just like one more time, right? Like this is 4 times, because that actually just is a sub k, plus 5 times 3 to the 2k minus 1. And then here, let me see if I can squeeze one more thing. Maybe by inductive hypothesis, what do I know about a sub k? I know it's like a multiple of 5. So it's, you know, it's like of the form 5m for some m, for some integer m. Okay, well, if a sub k is a multiple of 5 by my inductive hypothesis, then this really looks like 4 times 5m plus 5 times 3 to the 2k minus 1. And so now we really have showed, I just kind of went out to the bitter end here, we really have showed that this whole thing is a multiple of 5. That was it, right? We started. This is a little bit slightly disorganized, but I assumed that a sub k was a multiple of 5, and what I have just concluded down at the bottom of this board is that a sub k plus 1 is a multiple of 5. And now you should write the sort of concluding sentence, right? What we've shown is that a1 divides 5, and if a k, sorry, I just wrote that backwards. We showed that 5 divides a1, and if 5 divides a k, then 5 divides a sub k plus 1. So by the principle of mathematical induction, 5 must divide a sub n for all n. So it's like this, right? Here's the kind of concluding remark. A sub 1 is a multiple of 5, and for any k whatsoever, on the assumption that a sub k is a multiple of 5, a sub k plus 1 is a multiple of 5. So since it's true for 1, it must be true for 2, it must be true for 3, etc. By the principle of mathematical induction, every number of the form a sub n is a multiple of 5. Okay, goodbye.